So the assignment on Canvas, make sure that I believe I hit publish on it.
When I checked earlier, it was
It was up.
published, but I couldn't view it.
Okay, good to know. I try to take all those off every year, all the times, because the schedule just changes just enough. I can never rely on it being. So fix that up, and then there it goes. All right, so it should be good then. I'll get a printed copy of the report sheet and the spectra for you, but you can also just do it digitally if you'd prefer. But anyway, let's talk about the three. There's basically three main styles of 2D NMR that we're going to talk about. The first one is basically a proton NMR with another proton NMR. And so the normal way we do just a review of how we normally test or get the NMR data is basically you put it in a really strong magnetic field, right? So then everything with an odd number of nucleons winds up aligning to the magnetic field. And then you shine light on it, and that light gets absorbed depending on what wavelength it is, based on how much energy it takes for them to flip and spin, so that because in a magnetic field, all these odd numbered nucleons have, what's the phrase? They have two energy states. They have aligned with the magnetic field, and then they have opposite of the magnetic field. And they don't typically exist outside of those two states. So if we shine light on it, we can get them to flip from with the field to against the field, and then we watch them flip back, and that gives off energy that we can measure. So that's what's happening here is you let everything relax to become its lowest energy state, you shine light on it, and then you watch the signal come out. With a 2D NMR, you do two pulses with slightly different energies, and the amount of time you wait in between them is going to give you how coupled they are. All right, and we still collect the same data. It still shows up the same way as light being given off. And then mathematically, basically by doing that, we can take the signal that comes from T1 and T2, and we can do a Fourier transform with it. And that basically separates out the two spectra and allows us to see where they interact, where these matrices are interacting with each other. And if you haven't seen Fourier transforms, and you've talked about them at all in physics, or kind of, you don't need to know the mechanics of how they work, but basically it's a way of taking overlapping waves and separating them out into their distinct functions. So you basically, it's a way of taking a bunch of noise and separating it out into two signals instead of just one. And so where those two signals interact is what shows up in the 2D NMR when we do that. All right, so we get something that looks like this. And so the basic form where we proton NMR with other proton NMR is called COSY, which stands for correlation spectroscopy. And just like we mentioned last week, you can kind of see the next one has it zoomed in, but you wind up with this diagonal that goes, and also because we count NMR, zero is on the right hand side and it counts down, so it'll be the slope of the line will look like this. And so the way that this works, we have something like this molecule here. It's only got three distinct hydrogens, right? So we should see 3 signals. Well, 1, 2, and then the nitrogen one. And we actually do see. So this is the real data. So there is some impurity in there. I bet that this is acetone. Because it's not labeled down here. But just by looking at these peaks, we could probably figure out what goes where. But some of these are pretty close to each other. So trying to figure out which one's more de-shielded is a little bit tricky. Oops. We can just look at the proton NMR for the simple molecule. The methyl is a little bit more shielded because methyls typically are, right? Methyls are usually the furthest to the right. Then we have the amine down here. The amine's not going to show any splitting, just like with OHs. Because it's slightly different energy. There's also the reason why they tend to be broad and why they're singlets is because they're not attached to the same type of atom. So the spring constant basically between nitrogen and hydrogen is not the same as carbon and hydrogen. And so you're not going to see any coupling between the adjacent neighbors with nitrogens and oxygens. And that's why they qualitatively look different. They look a little bit broader than the carbon hydrogen bonds. When we look at the COSY spectrum here, we only see 2 signals. And they're only on the diagonal. Basically, we see A interacting with itself, C interacting with itself. Then B doesn't really interact with B at all. Because again, it's not a carbon bond. And so it's going to have a slightly different energy signals. If we look at a molecule that's a little bit more interesting, go ahead.
Oh, no, never mind.
So basically, if you want to see what's coupled with what, you just look at the rows and columns. The signal here is C, if you follow it straight down, where we see our signal right here, also matches up with the same peak on the other axis. So the proton NMR, the one-dimensional curves, they're measured separately and then overlaid so that we can do this basically. But that allows us to say, okay, this peak correlates with itself. Obviously, it should. A correlates with itself.
Really quickly.
Yeah.
Can you just briefly go over the 2 rapid pulses again versus in the very beginning? And how does that give us this?
It basically, because we do the 2 pulses, we don't fully allow the first signal to die out.
Okay.
So if the first signal is still going, when
Yeah.
the second signal hits, then those 2, you're going to get a mixture of 2 different waves on top of each other. That's why we need that Fourier transform. But the way that those 2 waves interact tells you something about how their energy signals are linked. And so a lot of times, the first thing you can do with these is you start by drawing your line, your diagonal, because that makes it really obvious what's not part of the diagonal. And what this really shows us is that if we don't have any signals off of the diagonal, that means that you don't have any carbon hydrogens that are adjacent to each other, which we can also tell by looking at this because of singlet, singlet, singlet. So, and even if we leave off the nitrogen one, we know that C doesn't have any nearest neighbors because otherwise it would see peak split. So if we look at a more interesting molecule that has a little bit less symmetry, nitrogen with 2 protons, a CH2, a CH2, and 2 methyls. If we look at this proton NMR, so this is the full one, this is just the zoomed in version of the same molecule. Once again, all the way down here, really weak and really broad, that's our nitrogens, our hydrogens that are on the nitrogen. And then here we have some peak splitting. So now we can say, okay, well, we definitely have some adjacent protons. So they should show up in the cozy spectrum off of the diagonal. We would expect this signal and this signal to be coupled with each other because they have some peak splitting, right? This we can be pretty sure is the methyls because one, it's if we look at the integration here, 3-to-1. And there's no peak splitting.
Is the difference there, because it's pretty stark, it's like 0.4 in the like shielding. Is that because the tertiary amine, like the electrons donating aspect of the carbon groups makes that more shielded, the ones that are next to it?
Yeah, I'm gonna.
That's just, I was kind of surprised by how big that difference is.
Yeah, so C is more shielded because those methyls are electron donating. They're gonna donate electrons to nitrogen first and foremost, but then that also, if we're comparing a nitrogen with 2 methyls versus a nitrogen with 2 hydrogens, obviously there's more electron density to go around.
So, okay, I'm just surprised by how big that difference was.
This is zoomed in too. If I go back to the first one, sure, it's still 0.4, but that looks a lot closer. If we're used to seeing the whole spectrum, not the zoomed in version as much. Right, and so what we would expect is on the cozy, then we do have some signals showing up, and that tells us that. So here's our diagonal. That tells us that peak B, or the protons responsible for peak B, must be adjacent to the protons responsible for peak C. Right, and there is splitting gets funky when you do this. It's almost like it gets rid of the n+1 rule. If you zoom in on that. You zoom in on that off diagonal peak, it looks like 2x2, which it's not as trustworthy as peak splitting, but that generally means you're gonna have 2 protons in each of our 2 neighbors for each of those signals. So it's telling you the same thing as the triplets. Triplet tells you 2 nearest neighbors. The fact that it's 2x2 means that both of them have 2 nearest neighbors. It's a little bit less strict, and so you can't trust it quite as much, but you always have the 1D NMR to look at as well. All right, and so B correlates with B, C correlates with C, D with D. And then those B with C ones. And the other thing to remember is that you only really need to look at one side of this. It's going to be symmetrical. So you don't really need to look at this signal here because it's the same as that signal there. If this is C correlated with B, this is B correlated with C, which should look the same. All right, so we go even bigger molecule. So now we have multiple. We have one signal we would expect to be coupled to 2 other signals. If we just look at the proton NMR zoomed in, once again, we can figure this out. This has got to be, just based on the splitting, it's got to be our central one. Then we have these 2, same difference, about the same shift, about a 0.4 shift again, which again makes sense. Directly adjacent to a nitrogen with 2 hydrogens versus it's the exact same, not the exact same, it's very close to the same environment. So the shielding should be close to the same. Right, and we do in fact see both of those, and we do see the 2x2 in those signals as well, which kind of makes sense because C has 2 hydrogens correlated with 2 hydrogens and 2 hydrogens correlated with 2 hydrogens. So we should see 2 2x2 matrix or little signals, multiplets. And we zoom in, but you can see how if you zoom in enough, you start to see other little signals built in there, so don't trust splitting, but it's just an interesting kind of artifact of the way these are measured. And then these are basically, those are not far enough off of the diagonal to be considered real signals. But it does look like it's showing up where the methyls and D would run into each other. And those aren't really close enough that we see much coupling, which is why there's such faint signals. So typically we can only see the nearest neighbors with cozy. There's a form we're going to look at in a little bit that specifically only picks up carbons that are 2 to 3 bonds away from a hydrogen. So it's very specific. These ones are a little bit looser and more short range. Right, so the way that we're gonna answer the questions about these is basically gonna be similar to what we're doing here. You get a figure, here's A, B, C, D, E. Look at the 1D NMR and assign it. Assign the peaks as best you can, and then look at the 2D NMR and see if B and C are indeed coupled like you expect them. And then C and D coupled as you would expect them to be. That'll tell you that you interpreted your 1D NMR properly. But considering we're starting from the structure, it's usually a good idea to look at the 1D NMR and do the best you can with it. Like, I'm pretty sure that these, get it down to a 50-50 shot for some of them, and then use the 2D NMR to find, put the nail in the coffin. HSQC, heteronuclear single quantum coherence spectroscopy.
Say that 5 times.
Right. There's a reason that scientists love their acronyms, because it's a lot better than the alternative. Basically what this does is this takes your carbon-13 NMR and overlays it with the proton NMR. So it's not as symmetrical, but it'll show whatever signal shows up in the proton NMR. Wherever you see those signals, that's going to tell you that it's related to these other carbons. All right, so if we look at carbon-13 NMR for the same molecule we already looked at. So this is the one with all the symmetry. We shouldn't see, the nitrogen's not going to show up at all. The proton on the nitrogen might show up in the proton NMR, but there should be no signal on the carbon NMR because it's not attached to a carbon. And then A and C are going to be the only carbon signals that show up. This is probably solvent. Based on where that is, maybe this is in benzene. Beside the point though, the fact that only these ones are labeled is telling you consider these to be the carbons that we care about. And really, if you're taking the spectrum for yourself and you don't know what it is, if you made the sample yourself, you know what the solvent is. If you know what the solvent is, you know what impurities are going to show up, because you never actually take an NMR of a pure substance. It's always a pretty dilute sample dissolved into a specific solvent. And so if you're living in this world, like, oh, 3 peaks that show up at 80, that's definitely this solvent. Maybe tetrahydrofuran, because there's multiple peaks there. Regardless, it's not labeled, so don't treat it like it's a significant signal. And then you remember when we learned about carbon NMR, there was that DEPT, which caused the signals to flip positive and negative based on how many hydrogens it had. The fact that our solvent disappeared when we did this tells us that our solvent has no carbon hydrogens on it, or that they're all sp2 maybe. Regardless, this does allow us to assign this. We have a methyl group, so that should be the one that still points upward. And then we've got our CH2, which should point downward. And if we look at the HSQC for this, we only see two signals. So because A is a carbon that has hydrogens and C is a carbon that has hydrogens, you need both of those to be true for it to show up as a signal. If you had a quaternary carbon, it would show up in the carbon NMR, but not the proton. If you have something that has hydrogens that's not a carbon, like our amine, you see a signal in the proton NMR, but not the carbon. So where signals aren't can be as helpful as seeing signals that are there. And so when we're looking at this, this allows us very clearly to say, okay, well, I already looked at the carbon NMR and I already assigned this the more shielded signal to be A, to be the methyl group. And then also the proton shows up there the same spot. Right, so it really is just allows us to do like a one-to-one mapping. If you either have the proton NMR that you've already interpreted, that allows you can basically use it as a Rosetta Stone sort of situation. But what I know what my carbon NMR tells me, that just allows you to one-to-one translate. You don't even need to think about the proton NMR because as soon as we say that this is carbon A, look where the signal shows up, that's protons A. Right, and again, no diagonal line here. We're not looking at them coupling with themselves, so the diagonal line doesn't mean anything.
Will there that would be a situation though where like as I feel like will all the points necessarily show up on a diagonal line though with this kind of thing? In the HSQC or
Not really. Let's look at the more complicated one here in a second. So this is just our asymmetric molecule. So now we should see three carbon signals, and then our amine. And same solvent peak here, so ignore the solvent peak. There's our three carbon peaks. We'd normally say, okay, D is going to be the most shielded, then C, then B. And if we look at the DEPT, D is pointed down, so I take it back. This first one, the most shielded, must be C. Right, because it's got to be a CH2. Because this is definitely D then, and that's B. We had B right, we just flipped C and D because I don't have my sheet. What's up? Long time last week. It's a little, yes, I did see that in the practice. But it's
also got paperwork I need to sign. Society money.
Yes, signing paperwork, here we go. This is for what?
Did you get your application in for adjuncting?
I did.
Awesome. Laura will help you with that. He's gonna be a new wheel.
Nate said that he was gonna
Justin.
Colette Minkoff. Starts with K, it's very long. It's funny because I kind of got the application, I turned it in like in October for the EMS department, and it won't let me like clear that and then put in a new application. So, yeah, so Nate told me that he would ask you today to pull it, so I don't know if you guys. Okay, or you ready? Awesome, look forward to it.
All right. So then when we look at the HSQC here, you see there isn't really much order to it in terms of a diet.
Oh, because all the shielding and stuff's gonna be different on both.
Right, especially since C and D are not where we expected them to be. D is the more shielded protons, but the less shielded carbon. So it's a little bit out of order that way. Right, because this is definitely D because there's no splitting, right?
Yeah,
But it's our signal that shows up for this column here. The strongest signal is the one that shows up here. And if we zoom in just on the B, C, and D region, we've got D correlated lower over here. So that was the middle peak on the carbon, is the most shielded on the proton. And then B correlated to B are most de-shielded. And then here's C correlated with itself. So more de-shielded carbon in less de-shielded protons. Oh, did I say that backward? More de-shielded protons, less de-shielded carbon. I still think I'm saying that backwards. I can't find where I'm saying it backwards.
yeah, I know, it confuses me, I'm like, which direction is shielded?
Well, in more de-shielded versus less shielded.
Right, yeah.
So I've been using double negatives. I'm confusing myself and everybody else. And you can kind of, if you imagine this topo map, you can kind of see a little bit like that kind of looks a little bit like a triplet, but not really.
Yeah, it's, yeah.
So definitely one of those where look at the shielding up here. And then there, I guess this is also a good time to see and yeah. There's a concept that we didn't really talk about very much, called coupling constants for these one-dimensional proton NMRs. The coupling constants are basically like a more low-tech way of doing cozy. The coupling constant, just because the report sheet asks you for this, your coupling constant is basically what's the distance between the splitting, between the peaks within the same signal. And the reason that winds up being useful, and the way we would write that, so if we were talking about that coupling coefficient for C and B. C and B are going to interact with each other here because they're adjacent to each other, right? So they would show up on the cozy spectrum. The coupling coefficient, like I said, is literally just the distance in between these. And it should be the same for both of them. If B and C are right next to each other, they should show up in the cozy and they should have the same coupling coefficient. So some proton interactions will create a wider splitting. The peak itself or the multiplet itself will get spread out more depending on that coupling. And so that's why we measure the coupling coefficient. And literally you just get as zoomed in as you can and look at, you know, it's 0.05 maybe is the difference. You literally are just looking at the numbers between those peaks. So go back to one of the ones that's just pure. Where is one of our proton ones? It's nice and zoomed in. I guess that's as good as we're going to get. So if you look at this peak here at 2.7 and 2.7 or 6.7, that's going to give you a coupling coefficient of 0.03. And again, B and C are coupled, right? Well, C is going to be tricky because it's got multiple splitting, but the distance here should be about the same as the distance here because they're coupled. But you can see how with C, that's going to get tricky because it's going to be coupled to D as well, which usually means all three of them will have the same coupling coefficient. And so you can use the splitting and say this one must be the one in the middle because it has more nearest neighbors. But just so you've seen the coupling, it's talking about the coupling constant is a little bit outdated now that we have cozy because You don't really need that when you can get this. That's a smoking gun. You don't have to measure the distance as much anymore.
So cozy is basically telling us which hydrogens are coupled to one another. And
Which means close to.
right, and then the HSQC is telling us basically which carbons correspond to which hydrogens.
Correct.
Okay.
And I've been harping on, it's not necessarily going to give you the same order, same diagonal, because you can have them offset with C and D being out of, quote unquote, out of order relative to each other.
Two different.
Two different variables, yeah. All right, so one more for practice. This one is our larger molecule that's got 4 carbons plus an H2. So we should have 5 signals in the proton and 4 in the carbon. Here's our DEPT. So that tells us right off the bat, that's E right there. But this being methyls, we can also probably assume E is going to be out of order relative to this when we look at the proton, because methyls are always the furthest to the right when we're looking at proton. So it's going to be another one that's a little bit different. And then as far as B, C, and D go, we could make the educated guess that this is going to be B. We would assume then that this is D and this is C. C should be the most shielded because it's not next to any electronegative atoms. But if we're not sure about that, we look at the HSQC and the proton NMR.
Oh, yeah.
We can say, okay, well, the only one we were really able to do on the carbon NMR with certainty was E. And that does tie up to a methyl, although it is more de-shielded than we were used to thinking. C is the most shielded out of the carbons. A doesn't have anything in here, which is what we expect, right? The absence of the signal for A tells us very definitively that's definitely my amine hydrogens. And if we have an alcohol, it would be the same thing. An alcohol is going to have a if it shows up, it'll have a weird looking broad signal with no splitting, and then nothing in the HSQC section.
And here it's just a methyls bonded to nitrogen, which is slightly more electronegative than carbon, so it's
Right.
shielding.
Exactly. Normally, we would expect methyls to be all the way over here, but because the methyls are attached to a nitrogen, it pushes it that way. So C is our CH2 group that is the most shielded, which also corresponds to the most shielded carbon in the carbon, which is kind of what we expected. But then B and D, okay, most D shielded should be B. That actually shows up a little bit higher than you would expect in the carbon. So this is one of the reasons why it's good to have this, is because you could figure all this stuff out without having the 2D NMR, but it's really nice to have that confirmation that we're actually interpreting these things properly. All right, so here's just the zoomed in version so that we can see everything a little bit more detail. So B correlates with B, D with D. There's E. Just another way, now we have more ways to put the pieces together, more pieces of information, make everything make sense. All right, last one. This is the trickiest one. HMBC is heteronuclear multiple bond coherence spectroscopy. This shows specifically, so HSQC shows you protons that are directly attached to those carbons. HMBC shows when protons and carbons that are 2 or 3 bonds apart. So not 1 bond, not 4 bonds, 2 or 3 will give you a signal. And that counts the hydrogen bond. So. If we just look at propane.
And that's with signal bonds, right? So if there's like a pi bond, a double bond, that's just counts as one.
That still just counts as one. Yeah. So this hydrogen, one bond, two bonds. So this hydrogen will show up on HMBC as being correlated to this carbon and this carbon. Right, but not the carbons directly attached to it. So this really does start looking like one of those logic puzzles from 5th grade. Like Jimmy is taller than Steven, but not as tall as Quentin.
Yes.
And you get the yes here, no there, put it all together to get something coherent out of it.
Then before you know it, you look like Charlie from It's Always Sunny with the.
Right, exactly.
Oh, yeah.
So here's our first molecule, same molecule we looked at before. 3 proton signals, 2 carbon signals, and some impurity. The protons on A, so it can be helpful to draw in the hydrogen. 1, 2, 3. So the protons on A should be correlated to the protons on C.
Yeah.
So A correlated with C, but not with itself. So A to A, there's nothing there. A to C, there is. C should be correlated to, so 1, 2, to the carbon it is attached to, kind of, but because it's symmetry.
Yeah, but not.
But not. So C should have 2 signals because there's that carbon that it can connect to, and there's that carbon that it can reach within 3 bonds. Right, so the number of signals is going to tell you this. This is one's really helpful for figuring out substitution on aromatics.
Oh, okay.
Because if you got a proton on a benzene ring that has just 1 signal, that means it must be the 2 carbons that it can reach must be symmetrical to each other.
Gotcha.
Right, so the number of signals winds up being useful. So A is correlated to C.
And then there's just some random noise going on.
Yeah. So this is with it drawn out in more detail.
Nice.
There are no carbons 2 bonds away. That's the other trick though, is you can't tell the difference between a carbon that's 2 bonds away versus 3 bonds away. They'll both show up as a signal. So we don't have a way to figure that out. So there's our 1, 2, 3 bonds. Right, so that's going to be protons on A correlated with carbon C. So, and then carbon or proton C can correlate with carbon C. So we see a signal here. And also carbon A. When we get our molecule with less symmetry, things are going to start looking messier again. So for hydrogen B, you can get to one bond, two bonds. So there's one, but then it's a nitrogen, so there should only be one signal for in the column, the proton signal. Look straight down, and it's correlated to C, but nothing else.
Cool.
After 3 steps away, there are no carbons. So, and then our proton C. 1, 2 bonds away. 3 bonds away is no carbons there. But there's these methyls here. So we should see 2 signals in column C. And they match with what we already established to be B and D. All right, so this is just if you already know the structure, this is just another way of cementing, okay, that peak that's at this many parts per million definitely is what I think it is. Right? This is too complicated to really work out the structure overall, but it can be helpful on those substitutions. Like, where is that methyl group attached to a benzene ring? All right, and so then our methyls takes 3 steps to get to the other methyl, or it takes 3 steps to get to carbon C. So you always start counting from the hydrogens on these, and the hydrogen's always going to be across the top. And so you just look at your structure, like, okay, I should see 2 signals in column B and see if it matches. Right, definitely one where you want to think about the structure before you try to interpret it, rather than while you're trying to interpret it. And then we start getting stuff like that. The bigger these molecules are, the more carbons are within 2 or 3 steps, right? So the more carbons you have within 2 or 3 steps, the more mess this looks. Right, and so the zoomed in version. E is our methyl. So hydrogen, 1, 2 to the other methyl or to D.
Makes sense.
So E, 2 signals. Itself and D.
Yeah.
D should then correlate back to proton E, or so 1, 2, 3 gets you to a carbon. 1, 2 gets you to a carbon. 1, 2, 3 gets you to a carbon. So we should see 3 signals show up in column D. 1, 2, 3.
So when we get the correlation on the HMBC between like an E and an E, something in itself, that means there's some kind of symmetry basically. So there's 2 identical
true.
groups bonded to the same atom in the middle.
Yeah, it's definitely a good flag to watch for.
There can't be anything else.
Right.
Otherwise it would be a different peak. Okay.
Yeah, it means you have to have at least 2 carbons with hydrogens on them that are equivalent to each other.
Yes. That is the much better way of thinking.
We have to be careful using the term symmetry in chemistry, because that has to do with the geometries,
Which this is.
and that's not what we're talking about.
No.
All right, and so then this is the last example. So 1, 2 gets you nowhere near a carbon. 1, 2 gets you to a carbon. 1, 2, 3 gets you to a carbon. So it should be 2 signals for B, C, and D. All right, and then we already talked about these other ones. I guess we can talk about C yet. 1, 2, there's a signal. 1, 2, there's another signal. 1, 2, 3, not a carbon. 1, 2, 3, not a carbon. So those ones shouldn't show up. And this is the one we did talk to. 1, 2, 2. There's a carbon. 3, there's a carbon. 3, there's a carbon.
And then here is it only the hydrogens that are bonded to carbons that we consider, so like the hydrogen A is the thing. You notice some ones bonded to the nitrogens. On the zoom in.
Yeah, let me go back to the less zoomed in version where we can actually see the nitrogen hydrogens.
It's not.
Yeah, there's nothing showing up here, right?
And that's that different spin constant.
That's, yeah. So you're just not gonna be able to get, because the nitrogen hydrogen is a different energy in that bond, different vibrations in that bond. It's not going to be able to couple to the carbons. So we're lucky we even get it to show up in a proton in a bond.
Okay.
Alright, so similar concepts to what we've done with NMR before, but presented differently. And actually, if you're used to proton NMR, 1D proton NMR, 1D carbon NMR, it actually just makes it make more sense, frankly, and gives you some absolute confirmation that you are understanding it the way you think you are. Definitely one where you're still going to want to have your cheat sheet pulled up for what chemical shifts for protons and what chemical shifts for carbon NMR are typical, so that you know what you're looking at. But your report for this one is basically what we just did. Here's a structure, here's a couple spectra for that structure, assign the peaks, and it even gives you the tables already formatted for you and everything. I actually really like this assignment, probably because I didn't design it and it's really well done. It came from, not that those two things are mutually exclusive.
But you didn't have to.
I didn't have to do it. It's really, really rare that I find an assignment that's really well designed that I don't have to tweak anything about.
Yeah.
So this one actually was published in Journal of Chemical Education. Actually had an article with this already ready to go, with slides already made and everything.
Oh, wow.
So,
If you own or if you buy the journal, you can.
so this is what I do is when I have 50 articles a year that I get with my American Chemical Society membership, which is, just like the professional society for chemists in the US. And I get 50 articles for free out of any of their journals, which is most of them. It's everything in chemistry that's short of like science and nature. Those are their own thing. But Journal of American Chemical Society, JACS, is one of the biggest chemistry journals in the US, and they have a ton of subsidiaries underneath them, including Journal of Chemical Education. So I just read through the table of contents every month and see, that looks useful. So if you want some printed copies, go to the library. Because my printer's still not working.
Okay.
But I would recommend printing out the report sheets. At least you probably don't need to print out the spectra, although you might find it helpful because then you can mark it up on the spectra. But the report sheet's what you're going to turn in. There's a separate PDF with all the spectra.
Cool.
Okay.
All right.
And then the slides are up there too, and I'll post a link to this video. If you need any.
Oh.